Today we are talking about how to calculate transpiration of fruit trees using the simplified approach that we published in 2013, Modeling Canopy Conductance and Transpiration of Fruit Trees in Mediterranean Areas, a simplified approach. In the past 30 years we have been lucky to have methods to measure transpiration in fruit trees, either using well lysimeters, like in this example, where we see pear trees at Irta and Lleida, and mostly using subflow methods, like this compensated heat pulse system installed in Olmos in Córdoba. Using this data, we have been working on transpiration models, and in any case, we start with the Penman-Monteith equation, the well-known equation, where we have climatic factors like net radiation, vapor pressure deficit, delta, which is a function of temperature, BPD is a function of temperature and humidity of the air, and two parameters RC and RA. If we apply the Penman-Monteith equation to a couple canopy like trees, we come to the imposed evaporation equation, where evaporation is proportional to vapor pressure deficit and inversely proportional to canopy resistance. When we apply that to trees, we have assumed that canopy conductance, Gc, is proportional to tree photosynthesis. The proportionality constant is the radiation use efficiency, and the amount of energy is given by the intercepted solar radiation. Then we acknowledge the response of stomata to vapor pressure deficit. In other words, stomata close as vapor pressure deficit increases, and using an equation like this, we arrive to this general equation of transpiration of trees, where the climatic factors affecting transpiration are solar radiation and vapor pressure deficit. Here, the coefficients A and B are empirical parameters. Q is the fraction of intercepted solar radiation. In other words, it gives us an idea of the size of the orchard. We have published a number of calibrated parameters for different species, like in this table, and the main advantages of this method as compared to others is that it does not require measurements of wind speed, uses solar radiation and BPD, and if we don't have them, we can estimate them roughly. And one important advantage is that the method allows adjusting to global change. The coefficients A and B are proportional to the ratio radiation use efficiency CO2 concentration in the atmosphere. For instance, if we increase CO2 concentration to 540 ppm, we will have to increase A and B by 20%. In other words, canopy resistance will increase. We have an Excel file that may be used to calculate transpiration using our method. We go to the Phytotechnia webpage at uco.es, and then inside the English version we can click on Excel file, calculation of transpiration of fruit trees using Villalobos et al. 2013, and then we download it. We open the Excel file, and here we have different weather data for day of year 180, summer, or 120, spring. We have values of maximum temperature, minimum temperature, maximum relative humidity, minimum relative humidity, and solar radiation for either sunny or cloudy days in summer or spring. These columns are calculated by the program going up to the daytime vapor pressure deficit, which is used in the equation. This is the value of the product of air density and specific heat capacity, and this is the calculated transpiration using this equation. Here, the inputs related to the orchard are the altitude and the fraction of intercepted PAR. Here we have the parameters for different species. We can change the species. Here we have the parameters for walnut. We can put here the parameters for any other species: apple, olive, apricot, peach, or pistachio. Atmospheric pressure is calculated by the program as a function of the altitude. And here we can change and put, for instance, 40% of fraction of intercepted PAR, and this would be the corresponding transpiration values.